Hello friends, welcome to Curious Mind. Today we're diving into the evolution of the semiconductor, the tiny engine powering today's technological revolution. From computers to artificial intelligence, from cars to televisions, and countless other devices we use every day. Semiconductors are the silent force driving modern life just like electricity. But how did it all begin? Let's trace the journey of semiconductors, from their fragile early days to the microscopic marvels shaping our world today. Before we go further, let's clear up a common confusion. A semiconductor isn't the chip itself. It's the material the chip is made from. Materials like silicon, gallium nitride, or silicon carbide have a unique property. Sometimes they conduct electricity, and sometimes they block it. That's why we call them semiconductors. On their own, they don't do much, but when engineers shape them into devices like diodes, transistors, and MOSFETs, we get the building blocks of modern circuits. When billions of these devices are placed together on a single slice of silicon, they form an integrated circuit, or IC. The microchips, also called semiconductor chips, that power your phone, computer, and car. Think of it this way: semiconductor material is like the clay. Transistors are the bricks made from that clay. And an integrated circuit is the house built by arranging billions of those bricks. Tons of these houses together form semiconductor chips. So, when we say semiconductors are driving modern technology, we are really talking about how these special materials are crafted into complex structures that make our digital world possible. So now let's go back in history to understand the birth of the semiconductor. We first need to look at what came before it: the vacuum tube. In the early 20th century, vacuum tubes were the beating heart of electronics. Their job was simple but vital. They amplified weak electrical signals and acted as switches that could turn current on and off. This made them essential for radios, early telephones, and even the very first computers. The very first computer machines ENIAC used by USA Army, built in the 1940s, relied on more than 17,000 vacuum tubes to perform calculations that would have taken humans months to complete. But there was a catch. Vacuum tubes were large, fragile glass cylinders that consumed huge amounts of power, produced intense heat, and failed every single day. Keeping a computer like ENIAC running meant teams of engineers constantly replacing burnt-out tubes. Clearly, technology needed something smaller, faster, and far more reliable. The seeds of that solution had already been planted. In 1833, Michael Faraday discovered that certain materials, like silver sulfide, changed their electrical conductivity with temperature, an early clue to semiconductor behavior. In 1931, Alan Wilson developed the quantum theory that explained how semiconductors work at an atomic level. And in 1940, Russell Ohl uncovered the p-n junction in silicon, the invisible boundary that would one day make modern electronics possible. The real breakthrough came on December 23, 1947, at Bell Labs. John Bardeen, Walter Brattain, and William Shockley created the first working transistor. Made from germanium, this tiny device could amplify and switch signals just like a vacuum tube. But it used mere milliwatts of power, switched instantly, and could fit in the palm of your hand. This invention marked the birth of the semiconductor era. For their work, the three scientists received the 1956 Nobel Prize, and the world entered the transistor age. As engineers built more and more transistors, a new problem appeared: connecting them all. Each transistor needed its own wires, and soon the wiring became more complicated than the circuits themselves. This challenge became known as the tyranny of numbers. The solution was brilliantly simple. Instead of wiring thousands of components by hand, why not build them all together on one single piece of semiconductor? In 1958, Jack Kilby at Texas Instruments created the first integrated circuit, a tiny chip made of germanium that combined a transistor, resistors, and a capacitor, all on the same slice of material. A year later, Robert Noyce at Fairchild Semiconductor improved the design using silicon and a new technique called the planar process, making mass production possible. Just a decade later, the Apollo guidance computer, which helped astronauts land on the moon, used integrated circuits with a few thousand transistors. By the 1960s, a new kind of transistor changed everything: the MOSFET, short for metal oxide semiconductor field effect transistor. Invented in 1959, it was smaller, cooler, and far easier to manufacture than anything before it. Most importantly, billions of MOSFETs could be placed side by side on a single silicon chip, a breakthrough that made modern computing possible. This gave rise to the microprocessor, the first true computer on a chip. In 1971, Intel unveiled the Intel 4004, the world's first commercial microprocessor. It contained just 2,300 transistors, Yet it could perform logic and arithmetic operations that once required an entire cabinet of circuitry. For the first time, a single chip could think, calculate, and control. The beginning of programmable computing as we know it. By 1978, Intel's 8086 processor introduced the x86 architecture, creating a design legacy that still powers billions of computers today, from desktops to laptops and even the cloud. As engineers continued to shrink the size of each transistor, chip performance exploded. 20 micrometers in 1968, 3 micrometers by 1977, 90 nanometers in 2003, and just 14 nanometers by 2014. Every generation packed more transistors, delivered more speed, and used less power. These microprocessors were the ancestors of today's semiconductor chips, the powerful silicon brains inside modern devices. The same principles that powered the Intel 4004 now drive the advanced processors inside smartphones, data centers, and AI supercomputers built by companies like NVIDIA. The microprocessor wasn't just an invention. It was the moment when silicon began to think, and the foundation of the digital age was truly laid. But innovation didn't stop. Instead of shrinking flat, engineers went 3D. The FinFET, with its fin-shaped gate, reduced leakage and packed more transistors. 3D stacking allowed microchips to grow vertically, layer by layer. New materials joined the race. Silicon carbide for high-power electric vehicles, gallium nitride for 5G networks, and experimental quantum and photonic chips that use qubits or light instead of electrons. Each new generation pushes the limits of manufacturing, with chip factories now costing over $20 billion to build. The challenges are immense, but the spirit of innovation burns brighter than ever. From fragile vacuum tubes to quantum chips, semiconductors are the silent engines of modern life. They power your phone, drive your car, run the internet, and guide rockets into space. The story of the semiconductor is the story of human ingenuity, proof that the smallest materials can create the biggest revolutions. And for semiconductors, this is only the beginning. Stay curious, keep learning, and never stop exploring the wonders of science. Thanks for watching, and if you enjoyed this video, don't forget to like and subscribe.